So we can use this probability distribution as is if all we want to do is calculate relative probabilities. But if we want to calculate things like the average probability or the probability of the percent probability that maybe we're between two different distances, then what we really need is a normalized probability distribution. And that's one where we've accounted for the size of k, because we need to adjust the size of k such that if we integrate over all possible positions, the probability equals 1. In other words, 100% probability. So in other words, if we look everywhere for Spider-Man, we have to find him somewhere because he exists. Okay, so we can symbolize this as saying that if we integrate our probability distribution over some volume element, we'll just, I'll put d tau as sort of an indefinite volume element, because the volume element is going to depend on which coordinate system we use. And if we do over all available space, in other words, if we search everywhere that Spider-Man could be, okay, so we don't have to search inside the treehouse because we know he's not there, he's locked out. If we integrate over all available space, this integral must come out to 1. In other words, the probability that he is somewhere has to be equal to 1. Okay, so let's go ahead and do this integral and figure out what the value of k is, because right now it's just an undetermined constant. Now to do this, we're going to have to use spherical coordinates. So spherical coordinates. So in spherical coordinates, we're going to imagine the position is being given by the tip of this vector here. And we can imagine that the vector is some length r. So let's go ahead and put that in as a variable. That's just the length of the vector. And that's the easy part. But there's also, we have to say where it is sort of in rotational space, right? So what direction is it from the origin? And the way we do that is imagine that if we tilt the vector up, so it's all the way pointing straight up on the z-axis, that would be a theta of 0. And then we can imagine it just sort of sagging down, this vector sagging down until it could fall all the way down to being on the negative z-axis. So we can see that theta is a value that could vary. So theta is a value that can vary. It could be any number from 0 to 180 degrees, or we could just say 0 to pi. It has to be somewhere in there. So phi is where we are relative to the positive x-axis. So we can imagine this is going to be increasing values of phi. We could go all the way over here. That would be 90 degrees to the backside, 180, and then 270, and then 360. Or alternatively, we usually use radians for this. So this would be all the way to pi and then 2 pi. Now notice when we measure phi, what we're doing is looking at a projection of this position vector onto the xy plane. So here's the xy plane, and we're imagining that there's a sort of shadow of this position vector on the xy plane. That's what this green vector is. And we're looking at that position. So within the xy plane, where is this green vector pointing? If it's over here, that would be 0 for phi. And then as phi increases, this green vector is going to start pointing in different directions on the xy plane. Okay, so phi is where you are on the xy plane, and theta is, are you pointing up, or alternatively, are you pointing down? So it could be any value from 0 down to pi, and of course phi, since it goes all the way around, it is any value from 0 to 2 pi. And just for completeness, we can say what r can be. So r, for any given problem, could in principle start off at 0. You could be right at the origin, or it could go off to infinity. Okay, so some number in that domain there. So r obviously has to be a positive number. Okay, so here's our review of spherical coordinates. The one tricky part of spherical coordinates is the volume element. Now the volume element is really simple in Cartesian coordinates. If we want to integrate over a volume, we just look at a little cube, and so it's going to be dx times dy times dz. But for problems with spherical symmetry, the Cartesian coordinates don't make any sense. It's a lot easier to write the integrals if we do them in spherical coordinates. And if you imagine drawing imagine taking a piece of eggshell that is a square. Okay, and then you say, okay, what's the volume of this little piece of eggshell? So you've got this distance, this distance, this distance, and then the thickness would be dr. You can see that using trigonometry, that basically this distance is not just a function of say phi, but also a distance from r, right? Because your actual distance is a function of r times phi. That's the way that radians work. So anyway, if you can figure out, and you can ask me in office hours if it's not clear, that the volume element, or look in your calculus book, it's all the same, that the volume element for spherical coordinates is a little more complicated. So we've got r squared, a sine of theta, d theta, and then a phi, and then a dr, and we can gather all the like terms later. But anyway, this is what it looks like. And we can use a 3D model in office hours, and I can show you, and it'll be pretty clear that this is actually the volume of this little piece of eggshell. So it's the volume that we're going to integrate over for spherical coordinates. So this is going to be the equivalent of what we call d tau on the previous slide. Okay, so let's go ahead, and given that this is dv, let's use this to normalize our distribution function. So remember, what we're trying to do is we're trying to say that the integral of the function times whatever the volume element is, we want this to equal to 1. Okay, so let's go ahead and write out our specific function. So our specific function is k times r to the negative fifth, and then we have our d tau, which is r squared sine of theta, d theta, d phi, dr. Okay, and right away we can see that we can combine some terms here. And the nice thing is that we can separate out the stuff that's dependent on phi from the stuff that's dependent on theta from the stuff that's dependent on r. So we can just combine those terms together. And when we do that, we're going to plug in some limits to the integral, because remember, there's some physical constraints on this problem. Okay, so first let's start by simplifying. So let's go ahead and combine all the terms that have anything to do with r. So we've got a kappa, or sorry, k, which we can just pull out. This is a constant. And then we've got r to the negative third dr. We've got a sine of theta d theta. And we've got a d phi. So this is actually going to be a triple integral. We have three variables that are all changing, so we have to separate out the terms. So we've got our r terms over here, we've got our theta term here, and our phi term here. Okay, now we have to put on the limits of the integral. Well, r can't be smaller than r naught, because that would be going inside the treehouse. So we've got r naught. Now in principle, r could be a very, very big number, because the probability of Spider-Man being someplace doesn't die off to 0 until you go to infinity. So let's go ahead and put an infinity here. So we're searching all the distances greater than r naught. So that's all available space. Now we have to do this term, sine of theta. Now if you remember, for spherical coordinates, theta can go from 0 all the way down to pi. And if we look at our problem, there's no physical constraints on the value of theta. So we're going to let theta go all the way from 0 to pi. And now we look at phi. Once again, our problem doesn't have any physical constraints on the value of phi. So since there's no physical constraints on the value of phi, we're going to go all the way from 0 to 2 pi. Okay, so we're going to integrate. Let's just work our way backwards. If we integrate phi, d phi, we just get phi. So we take 2 pi in for phi and then plug in 0, so 2 pi minus 0. Okay, I'll let you, as an exercise, integrate this. You know, if you integrate sine, you get the you get the cosine value. You got to plug in the pi and the 0, subtract them. Anyway, you end up with a value of 2. And then over here, doing this integral, this one we'll do a little slower here. Got our k, we've got r to the minus 3. So we know we've got to increase the value of the exponent by 1. And then divide by this value. So we're dividing by negative 2. And that's going from r0 to infinity. So to multiply that whole thing times this. So plugging in those values, we've got k, and then let's plug in the values here. If we plug in infinity for r, it's infinity to the negative 2, so that's going to be 0. And if we plug in r0, we have got negative r0 squared over 2. Times 2 times 2 pi. Oh, this is r0 to the negative 2. So we can see the negatives are going to cancel. We'll get a positive number. We can also just call this r0 squared on the bottom here. So we end up, and remember this whole thing is equal to 1. So we've got, let's see, we've got a k, negative times a negative is a positive. So we've got k times 2 over r0 squared. We still have this 4 pi here. It's all going to be equal to 1. We can cancel a bit. So we get k times pi, times 2 over r0 squared is equal to 1. Or we can say that means that k is equal to r0 squared divided by 2 pi. Value for k, we can write what we call a normalized probability distribution function. So before we had p was equal to k r to the negative 5th, where k was some undetermined constant. Now we know the value of k, that it's r0 squared over 2 pi. So we've got r0 squared over 2 pi r to the negative 5th, and this is going to give us the absolute probability for any particular distance from the treehouse for this for Spider-Man. So we're going to be using this in the next screencast to calculate an average value.